Okay, so let's get started. So we're going to be beginning this semester with talking about gases and liquids and a little bit about solids, but not so much about solids. Gases and liquids for sure. And so we're going to start with gases. This is chapter 10, the gas laws and gas properties. And so we're going to be going through all of these different things, and there's a lot of vocabulary in here too. So the volume is proportional to the number of moles, and so you'll see this idea of proportionality. And that's what this, it looks like an alpha, but it's not really an alpha. It's this proportional sign here. And that's all you need to solve some of these problems. I mean, you don't need the full ideal gas law. You could look at this, and anytime you have a proportionality, if you have before and after, you can solve the problem. Okay? So anytime you have a proportionality, you do what I call the ones and twos. So V2 over V1 is now equal to N2 over N1. You can turn any proportionality into an equation. Equation has an equal sign. That's what that means, equation. You can turn any proportionality into an equation by doing the before and after, the situation where you have situation 1 and situation 2. And most of the time you're saying, I've got a certain volume here with a certain number of moles, and then I've changed the number of moles. What happened to the volume? Makes sense, right? So you got before and after, and typically you have three knowns and one unknown, and since you have one equation and one unknown, you're good to go. Okay. We talk also about these terms like ISO, and ISO means same. So we have, this is volume. So if we had a line that went like this, that's called an isochore. And if we had a line that went straight along here like that, that's an isopleth, constant amount. And then we have, this is basically what we're dealing with. The number of moles is a measure of the number of the amount of stuff you have. You have more stuff, it takes up more space. And it's a linear relationship. Kind of like blowing up a balloon. If you put twice as much gas in the balloon, it'll be twice as big. Okay, that makes sense. Let's look at thermal expansion. So if you heat something up, it typically gets bigger, right? Especially gases, and it's linear. So this is a proportionality too. You could write V2 over V1 is equal to T2 over T1. We also have some isos on this one. So if we had, again, a constant volume, that would be like this. So that's an isochore. And then we could also have an isotherm. It's hard for me to draw straight vertical lines on this tablet, but that's an isotherm. And this line here, the gas phase region, that's the linear region where it behaves like an ideal gas, and it's volume is proportional to temperature. It's telling you that slope. Now, if we were to measure our gases, so here at 0C, 100C, if we measured our gas volume in boiling water, and this is what made it very easy to define like a standard temperature as ice water, 0C. You can take balloons and you can put them in a bucket of ice water, and you could measure the level, take the balloon out, maybe do a reaction in that balloon. The reaction volume produces a different volume. You put it back in that bucket of ice water, it comes to the same temperature as it was before. You can mark a different mark, and you can measure the change in volume with respect to that reaction. You could also change the temperature of that bucket and look at the change in volume. Now this is nice because let's say we measured the volume of our balloon in boiling water, and it's right here at 100C. We measure the volume of our balloon at ice water at 0C. When does that balloon go to zero volume? So if we extrapolate that line to where we go to zero volume, we end up with this minus 273.15 degrees C. So this negative temperature. What if we had a different amount of gas in there? If we had more gas in there, it'd be a higher volume. And what if we did the same experiment with that gas and we extrapolated? It would hit the same point. What if we had less gas? We put that through the balloon and this experiment, it hits the same point. So there's something interesting about this minus 273.15 degrees C. It keeps coming up. So we decided we don't like having negative temperatures. A temperature is kind of a measure of the energy in a substance. And so what does negative temperature tell you? It tells you there's negative energy? No, that doesn't quite make sense. So let's use a scale where there are no negative temperatures. So let's just move 0 from freezing water, because that was just arbitrary. It was convenient. Let's move that 0 from being freezing water down to this absolute 0, where there are no negative temperatures. And that's where the Kelvin scale came from. And so this is a nice little experiment to show how we came up with this Kelvin scale. So that's what's going on here. And that's absolute temperature. Okay. And so to convert from degrees C to Kelvin, you just add 273, and now you've got your Kelvin scale. So that's pretty straightforward. Okay, pressure is proportional to temperature, and it does the same thing. So if we had a fixed container and we cooled it to freezing ice water, you would have a certain pressure, and then if you boiled it, you would have a higher pressure. And if we extrapolate that down to 0 pressure, we get the same, negative 273.15 degrees C. And so this behaves kind of the same way. It gives us that same constant. We have some different isos here. Now we have a same pressure. That's called an isobar. And we still have isotherms too. So far everything's been pretty boring, just a linear relationship, proportionality. But now we get to pressure versus volume. This is inversely proportional. So this is what inversely proportional means. This 1 over volume. Okay. Now let's do our 1s and 2s, because this one's going to be different. Okay. So let's do P2 over P1 is equal to, now look where V2 is going to be. Like if I put a 2 on this P here, I got to put a 2 on that V there. So V2 is on bottom and V1 is on top. So when it's inversely proportional, it's flipped. Very important, because otherwise you're going to get it totally wrong. So that's how you deal with inverse proportionality. Okay, and now this is interesting. This is an isotherm, and look at the shape of the isotherm. This is at the same temperature. You have an isobar, which would be the same pressure. So this is an isobar here. This is an isocore would be here. And this isotherm, so the pressure and volume can change while the temperature stays the same. Okay. Now, I learned about Boyle's law when I took my scuba diving class. It was the law they talked about the most. Why would that be a concern for scuba divers, for Boyle's law? Yeah, you're breathing. How much gas are you putting in your lungs, which are about, let's just say, 4 liters, right? You got a 2-liter bottle on either side. Okay, so we got 4 liters of gas in our lungs, give or take. And you're down at really high pressure, okay? So at high pressure here, okay, I put in 4 liters of air at that high pressure, okay? In order to get my lungs to expand, my tank has to pump the air in against that external pressure because the water's pressing on my ribs. To get my lungs to expand, I have to put in a whole lot of gas at that high pressure to get to 4 liters. And if I hold my breath while I ascend, the pressure's dropping. And what's that gas doing? It's it's wanting to expand. If I go, in this case, this is a dramatic ascent from 40 psi to 5 psi. As the pressure drops, look what happens to the volume. It goes from 5 to 30. Okay, and that could burst my air sacs, and it's called an air embolism. So it can be really bad. So when you ascend from deep water up, if you've taken a breath at the deep water with a scuba equipment, you have to blow bubbles. You have to let the air escape as it expands. So it's kind of a weird feeling. You ascend and you're blowing bubbles out or letting them blow out. You don't have to exhale. It just comes out of your lungs as that air expands. And you're not exhaling, but bubbles are coming out of your mouth the whole time. Yeah, so it's kind of neat. You don't want to cut that off because then you'll build pressure up in your lungs and you can pop an air sac. So anyway, that was an interesting application of Boyle's law when I was getting my scuba license. Okay. So this ideal gas law combines all of these proportionalities. So let's look at them all. So this is the equation you want to memorize right here. PV equals nRT. And so this shows that volume is proportional to number of moles, that volume is proportional to temperature, and pressure is proportional to temperature. And that proportionality constant is this gas law constant, R. And also, if I move V to the other side, it's going to be in the denominator, and that's going to mean that pressure is inversely proportional to volume. So Boltzmann studied gases, and he gave us his Boltzmann constant. And then if you multiply that by Avogadro's number, that gives us R. So Boltzmann's constant times Avogadro's number is R in these units. 8.315 joules per mole Kelvin. And then if we want to get out of joules and into other things that are useful for us in the lab, like liters and pressure, atmospheres, we can convert that over and we end up with 0.08206 liters, atmospheres per mole Kelvin. Now you'll use that so much you'll probably remember it, but it's on your periodic table that you'll get for the test. So you don't have to worry about memorizing this constant, but you will probably use it frequently enough that you'll know it. But it's on there just so for you to check your work so you don't screw up or miss a zero or something like that, okay? So that constant's given to you on the exam. But these are essentially the same thing. They're all Boltzmann's constant with just different units. And so that's what this whole meme was about. It's like, find the difference between these two things. And she says they're the same picture because they're both Boltzmann's constant. Okay, just different units. So let's do some algebra practice. It's been a while for some of you maybe. And so let's solve for pressure. This is very simple review. So we want to get pressure by itself. And so I'm going to divide both sides by volume. And my volumes cancel. And so I've got pressure equals nRT over V. So remember your algebra. That way you don't have to memorize all these individual little equations. Now let's solve for volume. So we divide both sides by P. And these cancel. And so V equals nRT over P. Let's solve for the number of moles. So here we want N by itself, so I'm going to divide both sides by RT. And if I'm going too fast, that's why I video it. So you can go back and check the video if this was something that you wanted me to go slower on. So I have N equals PV over RT. And then lastly, we solve for temperature. We're going to divide both sides by NR. And their temperature is equal to PV over NR. So if you know algebra, all you need is the one equation, and then you can solve for whatever the pieces are that you need. Okay. So when you were back in the day saying, I'll never use this, you just did. Okay. All right, now this combined gas law. Sometimes we change the temperature and the pressure and want to know what happened to the volume. We'll change the volume and the pressure and want to know what happened to the temperature. So this is, instead of using those singular proportionalities where we just had V and T or P and T or P and V, we can use the ideal gas law and change everything and see what happens, okay? So here we have the ideal gas law. We can do ones and twos on the whole thing, and let's say we we wanted to see what happened to the pressure, okay? And we knew the initial pressure, the initial volume, the next volume, the initial temperature, the next temperature, but we didn't change the number of moles and we didn't change the gas constant. So we can just cancel these, and then we've got now this equation for pressure and volume and temperature. Okay, so if I wanted to rearrange that, I would pull the pressure over here on top, and I would take T1 over on the bottom and T2 over on top, okay? And so I would end up with P2 is equal to P1 times, and so T2 was in the denominator over on this side. It's going to be in the numerator on this side. So T2 over T1, okay? And then P went over here on this side. V1 and V2 are on the opposite sides as V1 on top and V2 on bottom. Okay, and so I know all of these. So now I can calculate what my P2 is. So again, a little advanced level of algebra, moving things around very quickly, but you can check my work in your notebooks. So let's do a problem with this. So sometimes I get in my car, especially after a cold front, and my little low tire light comes on, and it says you need to air up your tires. My manual says it comes on when the tires are below 25 psi. Okay, with the cold front that dropped it from let's see where we were. We were from 77 Fahrenheit dropped to 50 Fahrenheit. Wouldn't that be nice? Okay. Is this enough to take my 50 psi tire down to 25 psi? Okay. Do you have just an intuition whether it would be enough? I mean, it's a cold front. Maybe it's a coincidence and I've got a slow leak, or maybe it's the temperature difference that caused my tire pressure to drop. Okay. What happened to the pressure? It went from 50 to 25. That's a half, right? It dropped by half. To get the pressure to drop by half just with temperature, what would have to happen? The temperature would have to drop in half, okay? And it really didn't. It was at 298 Kelvin, and we always want to use the absolute temperature when we're dealing with these things. And it dropped to 283 Kelvin. That's not close to half. And so I know it's not just the temperature effect, okay? Now, I could have made a mistake. Maybe it wasn't at 50. That's what I aired it up at 6 months ago. Okay, maybe it was slowly working its way down. Anyway, but let's do the math. Okay, so we have 50 psi. 1 atmosphere is 14.7 psi. That's a conversion factor for you. It's also on your periodic table on the test. And so if you get a psi number on the test, you can use that conversion factor to convert it to atmospheres. We've converted to temperature, to Kelvin temperature in both cases. And so what we're looking at is we've got an unknown volume, the volume of my tire, and it's unchanged. We're making an assumption there. So look at my volumes. We're saying they're unchanged, so they cancel out. I'm assuming this is unchanged, meaning I don't have a leak, right? So I'm saying the number of moles is canceled out because I'm assuming it hasn't changed. The ideal gas constant is a constant, okay? So it doesn't change. It's in the name. And so I've just got the temperature effect. So I'm going to have P2 is equal to P1 times T2 over T1. So I've got 3.41 atmospheres. Actually, if we're not using the gas constant, this gas constant is 0.08206 liters atmospheres per mole Kelvin. Okay, and so if R doesn't cancel, then I have to change everything over to atmospheres. But since we're not worried about the using R, I don't have to have everything in atmospheres. I can use PSI in this case, because whatever unit I have for P1 is going to be the unit I get for P2. everybody see that? So let's use PSI. So I've got 50 PSI and 283 Kelvin over 298 Kelvin. Okay, break out the calculators. Three, enter 298, divide 50 times 47.5. So that's the temperature, the pressure I should have just by the temperature change. And so this tells me that I probably have a leak and I should go get the air compressor and fill it up and maybe even get it checked, run by Discount Tire. Okay. And so you'll catch me in my car, in the garage doing these calculations instead of just going to get the compressor and air it up, because in the end of the day, all I need to do is air it up. I don't have to do the calculations, but I can't avoid a good calculation. So, okay, so we did some temperature conversions. This is a good slide for you to bookmark or cut out, stick in your notebook, screenshot. These have the temperature conversion equations here. So if we want to go to Celsius, to Fahrenheit from Celsius, you can put the temperature in Celsius here. Okay, and this is the slope, right? 9 degrees Fahrenheit for every 5 degrees Celsius. Where did that come from? Well, let's think about this. We've got a temperature scale here of 0 to 100 degrees C for water. What's at 0 degrees C? That's freezing water. What's 100? It's boiling water. And we divided it in 100 units. It was actually made, this temperature scale was made based on water. Some people call it centigrade. Centigradations, or 100 gradations, 100 marks between boiling and freezing water. Okay, and then they gave it the name Celsius. Okay, but what is it in Fahrenheit? What's the top number? What's the bottom number? We know that one because in winter it's freezing. 32, right? 32. What's the top one? Anybody? 212. Kind of weird, isn't it? It's kind of random. 212. I don't know what Fahrenheit's actually based on. But the difference between this is 180 degrees. And the difference between this is 100 degrees. Let's see. And so we have 180 over 100. If we divide both of those by 20, we get 5. So we can cancel these and we get 9 up here. 20. So this 9/5 is just 180 over 100. It's just the conversion, knowing that water is the same temperature at boiling and the same temperature at freezing. And so we have the same temperature. 212 is equal to 100 and 0 is equal to 32. So that slope is a way to convert from Fahrenheit to Celsius. So if you ever forget the 9/5, you could redo this in your head if you'll just remember that water boils at 212. Okay, so that's where the 9/5 comes from. But there is this slope. So we correct for this the slope, and then we add this intercept, this 32 degrees Fahrenheit to get to Fahrenheit. We just undo that if we're going from Fahrenheit to Celsius. So the first thing we do is subtract the 32, and then we multiply by 5 and divide by 9 to cancel the Fahrenheit and get into units of Celsius, and now we're in units of Celsius. Notice the slope of Kelvin and Celsius is just a 1-to-1 change. So there's really nothing here except to just change the degrees Celsius to Kelvin and add 273. But that's the temperature conversion for Kelvin and Celsius. Going from Kelvin to Celsius, you just subtract 273 and then change the unit from Kelvin to Celsius and you're done. So that one's pretty easy. Pressure conversions. This is a good slide to have. We've got atmospheres to torr. A torr is the same as a millimeter of mercury. We've got pascals. Those come in a couple of times. And then PSI. And then bar. That's a new pressure unit fairly recently. And is atmospheres to bar. And then volume conversions, there's 1,000 liters in 1,000 milliliters in a liter, and so on. We've got inches, cubic inches, and meters cubed. So this is a useful slide for you. Let's see. Let's convert. I could do some unit conversion practice. Or I could go into the ALEKS practice. So this is a time where you guys get to choose. So what do you, is there a pressure unit or a volume unit you want me to convert, or temperature? Don't be shy, yes. Do one of the temperature ones? Okay. So pick a temperature you're curious about. Do you want to like start with a Fahrenheit temperature? Or what do you want to do? Start with Fahrenheit, okay. Let's see what like a comfortable temperature is. Like I like for sleeping, I like it a little colder. So I like 64 Fahrenheit. You know, that's why I set it's a good temperature to sleep at. Is it 64? That's kind of cold. Might be 74. Yeah, I don't think I pay the money for 64. I think it's 74 that's sleeping, maybe 72. Let's do 72 because that's going to be a good night's rest. So what is that in Celsius and then in Kelvin? So we've got 72 degrees Fahrenheit, and we want to. It's not real convenient to go straight to Kelvin from Fahrenheit, so let's go through Celsius. It's a little tedious, but it makes the most sense. And so which equation are we looking for here? We've got Fahrenheit, and we want to get to Celsius first. And then we'll go from Celsius to Kelvin. Okay, so we got 72. Let's do the minus 32. So it's 40 degrees Fahrenheit higher than freezing. Okay, let me make that little zero smaller so it doesn't look like a zero. Okay, and so that's we've done this first step, and then we're going to multiply by 5 degrees Celsius over 9 degrees Fahrenheit. And you see, follow the units. That'll tell you if you're getting it right or wrong. If the units don't cancel, then you're screwing something up. I know a lot of you, because I'll look at your work when you ask me for help, and I won't see units. And if you're lazy, then you're going to get confused and not know why you're wrong. So if you use the units, it's really very, very good. Okay, so let's do the calculator. 45 times 9 divided. 22.2. All right, so that's the temperature in Celsius. So if I needed it in Celsius, I'd be done. But we can just now go straight up and add the 273. So I'm just going to cancel that and make it Kelvin because they're 1 to 1, and I'm going to add 273.15. That's the actual absolute zero calculation. So 0.35 Kelvin, 5,789. So 295.35 Kelvin. That's good sleeping temperature. Sounds hot because it's 295, but that's a good temperature. Is that good? Yeah. All right, let's look at the ALEKS practice. We're about halfway through. We can come back to it. Well, we have to do some unit conversions in the ALEKS work too. So here's one using the combined gas law. Okay. And to be honest, I think ALEKS pushes you a little bit beyond what I would typically do if I were making up the problems. ALEKS adds a lot of little extra difficulty, like giving your temperatures in Celsius. So you have to do the conversions in the problem. It'll give you mass instead of number of moles, and so you got to convert to number of moles and so on. So there's a fair bit of work in ALEKS. That's why I say start early, because you got to do all those little conversions, and they take time. So don't procrastinate. So anyway, it says for many purposes we can treat propane like an ideal gas at temperatures above its boiling point. So its boiling point is minus 42 degrees C. This is another thing ALEKS does, and this is life, right? You get lots of data that you may not use in the problem. So you've got the boiling point of propane, but you're not going to use that in the problem. It's just information about where we are relative to its boiling point. Okay. So now the problem really begins. Suppose the temperature of a sample of propane gas is raised from minus 13 C to plus 13 C. And at the same time, the pressure is increased by 5%. Well, that's kind of weird. It didn't tell us the pressure. It told us how much it increased. And it told us in percent. So we got to figure that out too. So these problems are fairly tricky. So go through the explanations and so on. If you had a problem with this pressure, like DW, you asked me a question on email, don't say, I don't get this problem, with a screenshot. Tell me specifically. It's like, it's giving me the pressure in percent change. How do I deal with that, right? And that's a very specific question, and I can reply very easily with that. So the more specific the question, the more easier and fast the response would be. That'd also be something you could ask your TA or ask your study buddy. Okay, so let's go through this. This is how I would do the problem. I would get out of these Celsius temperatures first. Add 273 right away, and you get 260.15. And don't worry about trying to, it's good if you can keep up with me. I'm going to go fairly fast because it'll be on the video. Okay, so we added 273 to minus 13, so it went down to 260.15. And we added 273 to plus 13, and we got 286.15. So those are our temperatures in Kelvin. Okay, and then we got the ideal gas law. And so let's cancel all the things that don't change, right? So we've got a temperature change, but the constant, the gas constant did not change. We're assuming that the amount of substance didn't change, okay? And so what are we looking at? Suppose the temperature of the gas has raised, and at the same time the pressure is increased by 5%. Does the volume of the sample increase or decrease? And so we've got to look at the volume. So this is what we want to know, the volume relative to volume 1, okay? And we've got a change in pressure and a change in temperature. So those are our three variables, and we're going to solve for this volume 2. So moving things around, notice V1 went over to the other side on top. Everybody follow that step. V1 went across the equal sign and ended up on top because I multiplied both sides by V1. And the V1 on the left canceled and the V1 on the right survived, and so we moved it over to the top on the other side. Now T2 is still on top on that side. T1 is on bottom on that side. P1, since I'm moving across the equal sign, I'm multiplying both sides by P1, and so P1 ends up on top. And here, P2 ends up on bottom. It was on top on the left, now it's on bottom on the right because I divided both sides by P2. Okay. And so we've isolated V2, and we have everything else that we need on that side. Okay. So let's look at this 5% change. So we have the pressure that we had in P1 plus 5%. Does everybody see how that's a 1.05? This is the fastest way you can adapt to like percent changes. So let's say you put your money in the bank and you have 5% interest over the year. At the end of the year, you can multiply your money by 1.05 to see how much new money you have. Like you have your money and then you have the 5% more. Same with pressure. If we increase the pressure by 5%, we have the pressure that we started with, that's the 1, plus the 5%, 0.05. What if it said it was decreased by 5%? It'd be 1 minus 0.05 or 0.95. So if it went up, it'd be 1.0, however much it went up. If it went down, then it would be, 1 minus however much it went down. Just making sure y'all are good with that, because this is a fast way to do these percent changes. Okay. All right. So let's put this into our equation now. So we have our 1.05. So this is P2, right? This is our P2. So this P2 right here is now this. And now what do I have on bottom? P1. And I have on top P1. So those can cancel out. So see how I don't even need to know what pressure I'm at? I just need to know how much it changed. And so the P1s have canceled. And I've got 1.05 on the bottom. Now let's do the temperatures. Those are pretty straightforward. So I've got the 286. This is T2. This is T1. Because notice it went from T1 to T2. Okay. So those go in there, and I can do that division and divide by 1.05. And so this is the amount that the volume changed. So it went from V2 to V1 times all of this stuff right here. So this stuff is 1.047. So this first question, does the volume of the sample increase or decrease or stay the same? Increase would be 1. X, it increased, right? It went up. Decrease would be like 0.9x or whatever. Like it'd be less than 1. And stay the same would be 1.000. So if all of these numbers multiplied and they were exactly worked out to where it was just 1, so V2 is equal to V1 times 1. So V2 is equal to V1, there's no change. But if it's V2 is equal to V1 times some number greater than 1, it increased. If it's times some number less than 1, it decreased. And so that's the answer to this first question. So we would say it increased. And it says by what percentage? Well, it's this piece right here. That's the percentage change. So this is greater than 1, which means it increased. And so it went up by 4.7%. It's 0.047. And you make that into percent. You multiply by 100%. So it's 4.7%. Now, if you go through the explanation that ALEKS provides, it's pretty involved, and I think it's more involved than what I've shown. I've talked a lot about this, just kind of talking about each individual step. I did, but this was a pretty fast calculation. I just did 1.05 for the 5% change. I did the two temperatures, did the math, and I got 1.047, so it went up by 4.7%. Okay. Questions on this? This was not as straightforward as just giving the old volume and the new volume, or the old pressure and the new pressure. Okay, the percent change is a little weird. Okay, but it's very realistic. Yeah. Okay, let's do another one. So here, using the ideal equation of state. So this PV equals nRT. That's what this ideal equation of state is. This thing is PV equals nRT, that thing that you're supposed to memorize. Okay, so we'll do our temperatures first. So reaction between liquid reactants takes place at 20 degrees C in a sealed evacuated vessel. So they're sealed vessel and it's evacuated. So any gas above this is going to be from the reaction. And it's with a measured volume of 45 liters. And the measurements show that this reaction produced 29 grams of sulfur hexafluoride gas. So calculate the pressure of sulfur hexafluoride gas in this reaction vessel and ignore the volume of the liquid reactants. Okay. So we add 273 to 20 and we get 293.15 Kelvin. So that's our temperature. Here's PV equals nRT. And what are we looking for? Look at the problem. We look for the pressure. And so we're going to solve for pressure here by dividing both sides by volume. Okay, so the volumes cancel on the left and we have nRT over V. We also need to know, because this is number of moles, we need to know how many moles of this gas we have. We're given grams here. And so sulfur hexafluoride, this is where your naming from Gen Chem 1 comes in. We got sulfur. Okay, so that's a mass of 32. And hexa, what is that? 6. Fluoride, that's a mass of 19. So 6 times 19 plus 32 gives us the 146.06 grams per mole. Little side quest. Calculate the molar mass. Okay, and then we can We can solve for the pressure. So we know the number of moles from this molar mass. We know the gas constant. We know the temperature. And we know the volume. Volume, temperature, number of moles we get from the molar mass. So here we have 29 grams divided by the molar mass. So the grams cancel. And we have 1 over moles. And so that mole is going to come back up top. Okay. And then it's going to cancel with this mole. Okay. And then we have Kelvin here, 293.15 Kelvin. That's going to cancel. See how I'm using my units? And I know if I use my units and I end up with the unit of pressure, then I've done the problem correctly. So I know I'm getting the units of atmospheres. And the problem is asking for units of atmospheres. And so at least the units tell me I'm on the right track. Do all of the math and I end up with 0.11 atmospheres. So this is the ideal gas law equation. They're great. They're pretty straightforward, especially when you get everything into the units of the gas constant, atmospheres, moles, Kelvin, liters, and then it's pretty straightforward. It's all these little side quests that you have to take, like using the molar mass to calculate the number of moles and things like that. Questions on this one? It was much faster. Don't ask yourself if you understood what I did. Ask yourself if you would have known what to do at that point. Right? So it's very easy to watch me do problems. It's like watching your coach shoot free throws. It doesn't mean that when you're on the line, you'll be able to hit the ball at the basket. Right? So that's why you have to do the work at ALEKS. That's why I'm dedicating 35% of the course grade to ALEKS, because that's you practicing your free throws. Yes?
Does MW mean?
Good question. I will use MW or M sub W as molecular weight. Molar weight or molecular weight? So that's the MW that I will use typically. But the other phrase for that is molar mass. But I guess I'm old school using the word weight. Okay, so MW in my mind, that's what I immediately see that. I think, okay, that's the molar mass. But molar mass would be big M, little m, and I don't know if that would look as nice as MW. So molar weight is what I think of. Molar mass, molar weight, or molecular weight. So those are all going to be MW. So molar mass, molecular weight, all of those. And it has the units of grams per mole. The number of grams per mole of substance. And it doesn't have to be a molecule. It could be an atom on the periodic table. Like the MW for sulfur is 32, or fluorine is 19. Yeah. So MW, thank you. That would be the grams per mole of a substance. Perfect. Yeah. Are y'all comfortable with what I was doing with this mess down here? You know, I'm over here and I want to get to V2, so I just bring that V1 over on the top, on the right, and P1 ends up on the top and P2 ends up on the bottom. That's again, we're not showing the explicit multiplication of both sides by V1, but that's what we're doing. We're just cutting to the chase. So practice that. Look at the video. If you're a little sketchy on that, go ahead and do it the slow way. Multiply both sides by V1, both sides by P2, divide both sides by P2, multiply both sides by P1, and see how everything matches what I've got here. So prove it to yourself, and then you can get fast again, okay? And then let's do one more. We've got time. So here's a interconverting molar mass and density of an ideal gas. So this is an unknown compound vaporized at 110 C. The gas produced a volume of 1,880 milliliters at a pressure of 1 atmosphere, and it weighs 3.02 grams. Okay. So assuming the gas behaves ideally, that just means you can use PV equals nRT. Calculate the molar mass of the compound. So now we're calculating MW. That's kind of cool. In grams per mole. Okay. So we need grams per mole, and we've got grams already. So we need to solve for the number of moles. So that's the connection to the ideal gas law. We need N. And so we're going to take the mass and divide it by the number of moles, and we'll get the mass per mole. Okay, so let's find the number of moles. So we need to solve for N. And so moving again, so RT over here, this goes down into the bottom on the other side, and V goes into the bottom on this side. Wait, no, I'm sorry. I was solving for P for some strange reason. Okay, no, once I just move RT over to the other side in the denominator, I'm done. Okay, so N equals PV over RT. We convert that temperature to Kelvin. So we have 383.15 Kelvin. And we can put everything into the equation. So we have 1 atmosphere, which is right here. So this is P. This is V, but look what I did for V. This is 1,180 milliliters. And so I went ahead and made that 1.88 liters. Okay, so that's, for something that simple, I think you should be comfortable doing that. If you don't like that, you could do the full, 1,880 milliliters, and there's 1,000 milliliters per liter. Milliliters cancel, and I've got 1,880 divided by 1,000, so that gives me the 1.88. And that equals 0.0598 moles. Great, I got an answer on my calculator. Do not just go type that into ALEKS. Because this is the number of moles I have, and ALEKS is looking for grams per mole. So always follow those units. Don't, as soon as you finish a calculation, type it in and hit, did I do it right? Because you're going to get it wrong, and that's going to trigger 2 more times where you have to get this right. So we've got the molar, we got the amount of mass here. We're going to divide it by that 0.05. So let me erase my chicken scratch. So MW is mass per mole, and so it's 50.5 grams per mole is what this gas weighs. Okay. And so then that you put into ALEKS, you got it right. And it's kind of sad if you jump the gun, you did the problem right, or you were on the right path, but you typed in your answer too early because you didn't use the units. So once again, use those units so that you know that you're typing in the right number, what it's asking. Okay. So those are some pro tips on how to not get wrapped around the axle on ALEKS when you kind of know what you're doing, right? Use those units to give you a firm footing every step, and then you'll go fine. You'll do great. And that kind of meticulous behavior of always using the units builds good habits. Now, I've been doing this for 30 more years, and I still use my units because I know I don't want to make a silly mistake. Supposedly, they skipped a satellite off of Mars because they did a unit conversion twice. Like they didn't carry the units forward in their work, and they assumed that they had the wrong units, so they converted it again. And that double unit conversion was enough to throw the trajectory of the probe off, and they wasted all those billions of dollars. Okay, so that'd be something to look up. I heard that story, but I don't have a source for it, so who knows? Maybe urban legend.